Welcome to our webinar titled Earth Observations for Urban Greenery Management. Thank you for your interest in this topic. This webinar is a part of the EO4GEO project funded by Erasmus Plus program. My name is Maria Andrzejewska. I'm an expert in remote sensing and geoinformation, and together with my colleague Zbyszek.
Hello, my name is Zbigniew Szkop. I am an expert working at UNEP Great Warsaw Center, but also researcher at the University of Warsaw, and I specialize in urban greenery management, as well as assessment and evaluation of urban ecosystem services.
We'll try to present how remotely sensed data can support the management of greenery in the city. The whole webinar will last about 1 hour, not more than 1.5 hours. It will be recorded, and from time to time we'll ask you to answer short questions available in Slido. At the end, we plan to give you a floor in the question and answer session. But before we jump on our journey, let me start with a short introduction. Okay. Yes, so here you can see the agenda of today's webinar. We start with the introduction. There will be a part dedicated to the presentation of ecosystem services presented by Zbyszek. Then in the third part, I will save some basic information and background information related to the remote sensing and data which we will use, in which we were collected for the analysis we will describe in the fourth part, Warsaw case study, and then we end with question and answers, hoping that you will have some questions and will be able to answer, or opposite, you can have some comments, which are very welcome. So both of us are representing the UNEP Great Warsaw Center. That's an NGO created in 1991, embedded in the science division of the UN Environment Program. GREET belongs to the network of organization, global group of environmental information centers, experts in geoinformation, and known as Global Resource Information Database. That's the abbreviation. GREET comes from Global Resource Information Database. Since the very beginning, we are fulfilling the mission of the United Nations Environment Program here in Poland. This webinar is a part of the EO4GEO project, as I said in the beginning, funded by Erasmus Plus Sector Skills Alliance. And the Sector Skills Alliances are transnational projects which aim to tackle skill gaps in a specific sector. Our activities support the strategy for skills development and capacity building in the space geoinformation sector, supporting Copernicus user uptake and aiming in increasing the number of people able to access and use Copernicus data and information, as well as increasing the supply of skills to stimulate the growth of geospatial related jobs in Europe. Learning outcomes are presented on the slide. So at the end of this webinar, you should be able to understand how to acquire data on urban greenery using remote sensing methods, to understand how the data acquired can be used to improve urban greenery management, and to know the concept of remote sensing and where to look for satellite data. But before we move on to the substantive part of the lecture, let's answer the question why this topic of urban greenery management is important, especially in the context of adaptation to climate change. Cities and urbanized areas can be treated as areas particularly vulnerable to climate change and exposed to violent atmospheric phenomena and weather anomalies, which include floods and flooding, violent storms, urban heat islands, smog, thermal inversions, and also droughts. In the face of the growing threats related to climate change, in accordance with the recommendations and obligations arising from both global from all documents like global, international, and national strategic documents, there is a need to support activities aimed at adapting cities to climate change, for example, by increasing the quality and quantity of urban green areas. So let's say a few sentences about two such documents. The first, well known to everybody, I'm sure, is the European Green Deal. The subject of urban greenery management is strongly linked with the European strategic document setting out climate goals, including the climate neutrality, achieving the climate neutrality by 2050 and reducing emissions by 2030. The European Union's Green Deal strategy envisages achieving these goals by using resource efficiency from the transition to a clean and circular economy, reducing pollution and promoting biodiversity. Thus, it refers to the biodiversity protection activities presented in the EU Biodiversity Strategy 2030. How is this supposed to work in practice? The proposed EU Nature Restoration Plan envisages that cities with at least 20,000 inhabitants will develop urban greening plans. These plans should include tools to create biodiverse and accessible urban forests, parks and gardens, and other forms of greenery. They should also contribute to the improvement of connections between green spaces and eliminate practices harmful to biodiversity. As we can see, urban trees are an important element of international policies, also in the context of their importance for adaptation to climate change. Now, let's talk about how trees can do this. That is about the services they provide. Zbyszek, your turn.
Okay, thank you. So yes, exactly. Let's talk about these ecosystem services provided by urban vegetation and especially urban trees. So when we are talking about ecosystem services provided by urban vegetation, we are talking about something which each of us understands very well because we all benefit from it. When we go to the city park, for instance, to do some jogging, then we are choosing this place because in our opinion, it provides great environment to conduct this kind of activities. And if we are going, for example, to the city center, we want to walk along like roads, and along this road, there can be beautiful old oak trees, for example. And we want to do it just there because we enjoy the aesthetics of that place. So that aesthetic ecosystem services provided by these trees. And we could, I'm sure that all of us could mention dozens of these ecosystem services provided by urban vegetation and especially urban trees. But today, let's focus on 4, which in my opinion, they are the most relevant when we are talking about climate change mitigation as well as adaptation to climate change. And these ecosystem services are first carbon control, which is basically about sequestering and storing carbon. Second one is microclimate control, which is about reducing the scope and intensity of urban heat islands. Then the third one would be energy conservation, which means we are not only taking care about thermal comfort outside our apartment, but also inside our apartment. So we are reducing the amount of energy which we are using to cool our apartment and to heat them. And at the end, let's talk about stormwater control, which is important because it reduces the risk of flooding in our cities. So to start with, I would like to ask you a question, which is, I would like to ask you this question using Slido. So you can log in there on the website and put this code, or you can use QR code. And the question is basically, in your opinion, what is the most important ecosystem service of urban trees with regards to climate change mitigation and adaptation? I'm talking up here now at this point about these 4 ecosystem services which I just mentioned. So please log in or enter this website and put the code which is visible on the screen. I would like to know what's your perception. Obviously, there is no good or wrong answer, but it will be interesting to find out how do you see it. Maybe a few more answers, so I would like to wait a second. Please don't rush yourself, but it would be nice if you could enter. So as I mentioned, it's like you can do it using QR code, but the simplest way probably would be to visit slido.com and put, okay. Okay, great. Okay, maybe 10 more seconds and then we can proceed. Okay, thank you. I think for now we see already a clear leader here, so local climate control, which is very actually interesting for me to hear. So maybe we can go on with other slides, because that means that you are very well prepared also from that perspective, because very often when you are thinking about trees and climate change, most of the people automatically link it with the fact that, okay, we know that trees sequester carbon and they store it. So that's a very important ecosystem service. And indeed, nobody can deny that it's important ecosystem service. And it's what's more, we can easily measure it. So we know that 50% of dry weight of a tree comes from the CO2, which is in the atmosphere through the process called photosynthesis. But what is important here to know is that all this carbon which is stored when the tree is dying or when it's old enough and it dies, then obviously what happens is what happens with carbon stored in any other organism on Earth, including us, people. So the carbon returns to the atmosphere. And when we are talking about trees, we can make it like very fast. We can burn wood, for example. It can take longer when we leave wood to decompose in the forest, and it's the issue of months or years, or it can be even like years or decades if we make furniture out of it. But later, after this time, years, decades, the furniture also will burn out, and then basically we will dispose it. So we can burn it, or we can leave it to decompose. But at the end, the carbon which was sequestered will come back to the atmosphere. Does it mean that this is not important ecosystem of trees? Obviously not. It is very important, but because trees act as a carbon sink. So basically, because they store this carbon, it's not in the atmosphere, and therefore it doesn't cause the problem in terms of climate change. But it doesn't really matter if we are talking here about street trees or trees growing somewhere in the forest from perspective of sequestration and actual, because we have one atmosphere, right? So from that perspective, it doesn't matter because CO2 is gas and it mixes easily. But it matters from perspective that it's not the number of trees which counts, but the size of trees and how long they can store it. And then we know that urban trees are not the best here. I mean, for example, in Warsaw, we know that for street trees especially, which are growing in a very harsh habitat, if they live 20 years, 30, maximum 40, that's huge success. And the same trees growing in the rural areas, for example, could live like few times longer and accumulate more carbon. Not even mentioning that the price of the land out of the city is way cheaper usually than inside the city. So this is not an ecosystem service, which is crucial when we are talking about urban trees. We should rather focus on fighting with deforestation and so on, but it's not necessary for urban trees. But as you mentioned, which I was very happy to see the results of the survey, the trees can be great at adaptation to climate change. And one of the reasons is that we have very often in cities with especially hot climate, problem with urban heat island. And there are two main reasons why we have this problem. First of all, there is not enough vegetation which could provide evapotranspiration and therefore bring the temperature down in surrounding areas to this green infrastructure, we can call it. And the second reason is basically that because we have plenty of these impervious surfaces in the city, like concrete, like asphalt and so on, they are characterized by very low albedo, which means that the solar energy which is getting there, heating them, then basically they absorb it and they radiate it instead of deflect it. And here, obviously, trees are very efficient because they can, most of this energy, they can deflect. And therefore, our cities are not becoming hotter and hotter. But this is about thermal comfort outside in the city. But as I mentioned at the very beginning, we also can use it to make our comfort inside our apartments better. So for instance, if we have a tree which is providing shade, then inside of the building, we are able to go down with temperature, and therefore we don't need so much electricity to use to cool down. So we don't need air conditioning that intensively. On the other side, also, we can use trees to work as a, let's call it, windbreak. So basically, they're protecting our buildings from, in the winter time, when the very cold wind can hit the walls and make them colder, and therefore colder in the apartment. So we don't need to use so much energy at the end to heat this apartment. But we have to be very careful here, because it's not hard to imagine that we can get the effect which is the opposite of what we like to obtain. So if we have a tree which is providing shade in the winter time, and it's from the south side of the building, let's say, and therefore it's blocking the sun a bit, then we can cool down the temperature inside in the winter time, and we need more energy to heat our apartments. And some people would say, yeah, but it's not a big deal, because anyway, we are usually talking about deciduous trees which are losing their leaves during the winter. But it's not really true, because there are studies which show that still 30 to 40% of the solar radiation, it can be blocked even if there are no leaves, because of the other components of the tree which are still there. So it is an issue, and to make sure how to design the surrounding of the buildings in a way that is the most optimal from energy conservation perspective, and there are models and softwares which help us to do that. But very generally, we could say about for the cities like Warsaw, or basically Polish climate or climate in USA, it's very good idea in general, as I said, to plant, for example, these trees, deciduous trees on the side of the building, because then they can still block solar radiation in the very morning and in the very afternoon or evening, but it doesn't influence the solar radiation which gets to the apartment or the house during the winter time, because solar access zone is not that wide in the winter time anyway, so it wouldn't reach this point because obviously sun is lower on the sky during the winter. So that's one example. Another one example how trees can help us here in terms of adaptation to climate change. But the last ecosystem service which I would like to mention here is stormwater control. So trees can help here a little bit at least. So when we have parks in the city, so there is plenty of these pervious surfaces, and they actually are great at absorbing water. We have to acknowledge here that actually they are 12 times more efficient per square meter than having a tree. What does it mean? That if you would build like 1 square meter of impervious surface in the city, to offset it, we would need to plant a tree which has a surface of canopy of at least 12 square meters. So trees are not that much needed from that perspective of that ecosystem service in the parks in theory, but they can help here, because when the water is raining, when it's raining, the trees in the canopy, they can store some of this water before it goes to the ground, and then the rest goes to the ground, to the soil, and only when it's so, like it rains so long that it's saturated, then the rest goes as a runoff to the sewage system of the city, and then when it's like exceeding its capacity, then it can cause flooding. But trees help here because they have the storage capacity plus extra, they work as a specific pump, I would say. So they can absorb some water from the ground and conduct what we already mentioned before, this evapotranspiration. So that means that even more of this water can be soaked to the ground. But what is especially important, because as I said anyway, like pervious surfaces are quite good at absorbing water, but what is very important is when we don't have them, but we have impervious surfaces like streets, like parking lots, and then sometimes we cannot get rid of them. All of us like to have roads in the city, right? But then trees can help us here. When we plant them on the side of that road, then at least this part of the rain, which would immediately go down and go as a runoff to the sewage system and could potentially cause some flooding, then they store this amount of water and it causes less problems. So that's another ecosystem study. So we see that basically to make, and we are only today talking about these 4 ecosystem services, but as we mentioned at the beginning, there are dozens of them. To make sure that we create city which optimally provides these ecosystem services and it's the best in the perspective of making the quality of life people living in the city as high as possible, we need plenty of data. We need data about impervious surfaces, we need data about location, specific location of the tree, about its health, about species, and so on and so on, how they're located towards the buildings, the distance to the buildings, etc., etc. How to get this data? Usually how we get them is by conducting tree inventories in a field. So we go from tree to tree and we measure this, we investigate that. I mean, that's how urban greenery managers are doing very often. But we have a problem here. It's very expensive and time consuming. So for instance, in Warsaw, we have around 9 million of urban trees. If you would like one person to conduct this, to do this job, which we know it takes around 15 minutes for one tree to do proper evaluation or inventory, that would be approximately 1,200 years for that person. So it's a really long amount of time. We wouldn't go for this option, obviously, but alternatively, we could hire 1,200 people to do this job in 1 year, but then the cost would be like 80 million Polish zlotys to pay them for that, which is like 18,000 million euros, which is plenty. And there is not too many cities in the world which could really think about paying this amount of money. I would say none of them. So we see that this is a problem, but additional problem is like, even if we do it, even if some people, some mayor would be crazy ecologically into it and they would say, let's do it, still we have a problem because not all of the trees can be evaluated because we have the issue of having private areas which we don't have access. So we cannot measure trees there. And also because there'll be so many people perceive trees quality and so on differently. So the database wouldn't be fully objective. And out of this, because as I mentioned at the beginning, urban habitat is so complicated, so harsh for trees. Trees don't live too long. They change rapidly within 3 years. Therefore, we would need to conduct it every few years. So that's pretty much not an option. So the option is to have very local inventories and don't have full information, and then the management is not optimal, but it's good enough, and that's what's happening in most of the cities now. Or alternatively, we could use new technologies which can give us better information, and about that, now Maria Andrzejewska will tell you what that can be.
Thank you, Zbyszek. Thank you, that was extremely interesting for me as well. So now we really know what that trees are very, very important, and that we in fact cannot survive with the green areas in the city, living in the city. And that on the other hand, that we need lots of data to analyze or maybe starting from the beginning, that to manage the green areas in a proper way, we need quite a lot of data, which cannot be easily easily collected with the use of, only with the use of in situ inventories. So we are coming here to the main topic, or maybe those the second of those two main topics of today's webinar, to think what are the advantages of using remotely sensed data for the management of greenery management. What are the practical applications and adaptation in the context of adaptation to climate change, and that's the type of knowledge which you should get from this part of the webinar. But before we start, let me ask you to use this slide again. Okay, what's your knowledge in the field of remote sensing? So some of you has already answered. Yeah, please, I'm waiting for more. We have more than 40 participants, so hopefully most of you can answer the question, what is your knowledge in the field of remote sensing? That will help me in the way I'm gonna to present you the information. But I see that most of you have just the basic knowledge in this field. And we have also one person who doesn't know anything about remote sensing. Okay, let's go. So for those who are professionals and have advanced knowledge, so please forgive me that I'm talking about such details, but I see that half of our participants still have a basic knowledge. So let's go and let's look for some information about the remote sensing. Remote sensing is about measuring objects from distance, means devices are not in a physical contact with the feature. Remotely sensed data, in contrast to data collected by traditional methods, are collected by sensors installed on satellites, aircrafts, drones, but also in situ data can be collected with the use of remote sensing methods. We have two types, passive and active sensors. Today, I'm going to talk about these passive remote sensing sensors, which register amount of electromagnetic spectrum reflected by an object. Registrations are not limited to only visible part of the spectrum, like our eyes are, but to a broad range of spectrum, and we'll talk about this a little bit later. Registered data are processed in the dedicated software like image processing and GIS, which are translating the data into information on vegetation, temperature, elevation, and many, many others. Quite a long list. In our webinar, we'll focus on environmental applications, particularly on the green infrastructure in cities. There are many benefits of using Earth observation. First of all, it's low cost of information acquisition, so that's relatively cheap for the user, because we'll talk about the data which are completely free for the user. There is a spatial continuity of the provided data, their objective timeliness, and in the case of most of satellite data, regular acquisition at equal and short time intervals, which allows to study of changes occurring in a time. Earth observation is a unique source of information. It's reflecting the current state, is available to the public, is objective and continuous. It can be used by administrations and other users across countries, regions, cities. Everyone can have access to this, and in fact, everyone should use it, because most of our activities are related to the to the area. So they have we use the location, and we speak about with the use of the location. So we also relate some statistical data to the location, to regions, to administrative boundaries. So that's the use of and access to such data should be promoted. Information obtained from Earth observation can be processed and classified automatically and integrated with other spatial data in order to perform the in-depth analysis in social, economic, and environmental context. Some satellite data are available completely free of charge. Some have to be purchased. Just a few words about the history. The first Sputnik 1 was the first artificial Earth satellite, which was launched by Soviet Union in 1957. Next big step, I'm not presenting you the whole history with details, so just the, let's say, main steps and the most important points in the history. Then the next big step in the history of Earth observation was the launch of the first satellite under Landsat mission. It was 1972, which was operated by NASA and USGS. Since then, every few years, new satellites are placed in the orbit, answering the needs of governments, science, and industry. Copernicus program, which in 2014 replaced GMES program. GMES, that's an abbreviation from Global Monitoring for Environment and Security. And as you see, GMES was launched in 1998. So in 2014, Copernicus replaced GMES. And that's the European Union's Earth observation program, which is focused on collecting data about our planet and showing the environmental benefits for all European citizens, coming from the use of Earth observation data. It offers information services that draw from satellite Earth observation, but also in situ non-space data. Copernicus program is financed by the European Union, managed by the European Commission, is implemented in partnership with member states, the European Space Agency, and a few other dedicated agencies. Earth observation satellites, which provide the data exploited by the Copernicus services, can be split into two groups of missions. First, these are Sentinels. And there are several Sentinels, satellite called Sentinel. Sentinel 1, 2, 3, and 6 are dedicated satellites, while Sentinel 4 and 5 are instruments on board other weather satellites. Then we have also contributing missions, which are operated by national, European, and international organizations and already provide data for Copernicus services. With the technology development, the remote sensing sensors are more and more advanced and improved in terms of parameters like spatial resolution. So each year we are getting new sensors which are collecting with better and better resolution. And there are also quite a lot of satellites which are commercial satellites and achieve a spatial resolution even less than 1 meter. Here you have a short list of those, the most important and the most popular satellites collecting the very high resolution data. The data characteristics. Remote sensing is the process of detecting and monitoring physical characteristics of an object by measuring the amount of reflected electromagnetic spectrum. That's for the passive instruments. No matter if the data is acquired from a satellite or airborne level, its characteristics are very similar and include the height and orbit parameters, scene swath, and 4 types of resolution: spatial, spectral, radiometric, and temporal. In order to select remotely sensed data for your specific needs in a proper way, it's good to understand what those basic parameters mean, and we'll discuss it on next slides. Spatial resolution, that's the easiest and in most cases one of the most important. It refers to the dimension of the pixel representing the area covered on the ground. Higher resolution means better feature quality, but it means also bigger raster file size. We have to carefully select images as the resolution should be appropriate to the application we want to work on. That's like with your phone cameras. Those registering higher resolution show more detail, but the size of the file is much, much bigger. Thus, for analysis of the whole region, we should rather not look for images with the very high resolution, but to leave those very high resolution data for analysis of more local or smaller areas. So sometimes, even if we think that the resolution 50 meters or 30 meters is not good enough, but in a moment when we are gonna to analyze the whole region, the whole voivodeship, so then it's much better to work with this type of data than to go to data which have a 1 meter resolution. On the screen, you can see the Wimbledon tennis complex, which appears at different resolution depending on the satellite and sensor. Then we have a spectral resolution, which refers to the spectral bandwidth and the number of bands. The interesting thing is that they are not limited to the visible part of the spectrum like our eyes are. We can derive a lot of interesting information from this part of the spectrum, but there is much more beyond that. We register the amount of energy reflected in selected parts of the spectrum to further analyze the object based on its spectral responses in different parts of the spectrum. Quite often we are using the infrared part of this spectrum, especially for analysis of the vegetation. So most passive Earth observing satellites have between 3 to 11 bands, but a satellite called MODIS has 36 bands. Different spectral responses of objects by bands are the starting point for all analysis focused on type or condition of green objects as an example. So different spectral response of object is different in different parts of the spectrum, allow to identify and analyze the condition as well other parameters of the object. While the arrangement of pixels describes the spatial structure of an image, the radiometric characteristics describe the actual information context in an image. Radiometric resolution is the capacity of the instrument to distinguish differences in brightness levels of reflectance. The greater the radiometric resolution, the more accurate the image is. Radiometric resolution is expressed as a bit number. The maximum number of brightness levels available depend on the number of bytes used for representing the recorded energy. Thus, if a sensor uses 8 bits to record the data, there would be 256 digital values available, ranging from 0 to 255. So we can, on such images which are collected with the sensor, 8-bit sensors, will have 256 shades of gray. Temporal resolution refers to the concept of revisit period, which refers to the length of time it takes for a satellite to complete one entire orbit cycle. The revisit period of a satellite sensor is usually several days. Temporal resolution is also called revisit capability. The temporal resolution depends on the height and orbit of the satellite. And for such a satellite like Landsat, it takes 16 days. But for Sentinel-2, where the temporal resolution of Sentinel-2 constellation is 5 days. In Sentinel-2, we have two satellites, Sentinel-2A and Sentinel-2B. Each of them has a temporal resolution of 10 days, but because they work as a constellation, so then due to that, we have this temporal resolution much lower, so 5 days. Spectral characteristic of features may change over time, and these changes can be detected by collecting and comparing multi-temporal imagery. By imaging on a continuing basis at different times, we are able to monitor the changes that take place on the Earth's surface, whether they are naturally occurring or induced by humans. There are many satellite image viewers where you can view or even download satellite data for your own needs, free of charge and without limitations. Data registered by Landsat, MODIS, Sentinel are available as open data. Please note that on this slide, we listed just not all browsers, but that's just an example of EO browsers, so there are many more. Of course, there are data which are not available for free, but with the use of those browsers, you can look for data which are available free of charge. The functionality of browsers is simple, doesn't require any sophisticated technical knowledge. Most often the acquisition of satellite data is done in 3 simple steps. You select an area of interest, you select satellite, you select time range, and the cloud coverage. That's very important because in those types of sensors, which are passive sensors, and which are recording the electromagnetic response of the object. So if there are clouds, the response cannot be registered properly. So we try to look always for the cloud-free or the images which has quite a low level of cloud coverage. After setting all parameters, you can browse the resulting data. Quite often they are available in different combinations, so you can look at the data coming from the visible part of the spectrum, or you can look also at compositions which are false color compositions, so compositions based on the use of with the use of, let's say, infrared spectrum, part of the spectrum. On this slide, we can see other examples of 2 products of image processing. One of them on the left is the NDVI indicator, and which represent the quality of vegetation, and on the right is global and cover classification, which is a result of automatic classification of satellite images to several and cover classes. Both of these images are based on Sentinel-2 data. Open access to this type of data means that we don't have to learn about the techniques of image processing, but it's enough that we know where to look for this data and understand how can we use this data to our own needs. So this type of information which you can get just looking into the browser and browsing the compositions prepared by or coming from the services served by other institutions, they are a starting point for deeper analysis. In the context of vegetation studies, a dedicated satellite in Copernicus program was launched, Sentinel-2. The Sentinel-2 mission is a constellation of 2 identical satellites in the same orbit. It aims at monitoring variability in land surface condition, and its wide swath, which is close to 300 kilometers, is quite broad. The high revisit time, 10 days for one and 5 days for the constellation, support monitoring of Earth surface changes. Main applications include agriculture, land ecosystem monitoring, forest management, inland and coastal water quality monitoring, disaster mapping, and civil security. The spatial resolution, as you see, that's 10 meters in the panchromatic band and 20 meters and 60 meters. So we can use, there are several bands, and thanks to this type of data, we can really create information which is crucial for many applications. We'll talk a little bit about also Copernicus services on the next slide, I think. Yeah, so in addition to the satellite images of the Sentinel mission, Copernicus also offers ready-to-use products served by Copernicus services, which can be quite useful in preliminary analysis of urban greenery. First, which I'd like to show you, that's the Urban Atlas. It is just an example, of course. Urban Atlas provides reliable, intercomparable, high-resolution land use and land cover data for 785 functional urban areas. It is quite a huge database containing urban areas classified into several land cover classes. And for cities, there are 17 classes. For suburban and rural areas, 10 classes. The minimum mapping unit for urban area is 1/4 hectare, and for rural areas, that's around 1 hectare. The Urban Atlas is regularly updated. So the most recent edition, that's the 2018 edition, includes the database of land cover. The database of land cover changes between 2012 and 2018, and also revised layers of the 2012 Urban Atlas edition, but also a street tree layer. The street tree layer is a separate layer from the Urban Atlas. It includes continuous rows or patches of trees covering 500 square meters, quite small areas, and more, and with a minimum width of 10 meters. So it's quite a detailed database, quite useful for the also management of greenery in the city. Layers presented in vector form enable estimation of urban greenery areas and analysis of the structure and ecological connections between greenery patches. Within the Copernicus Land Monitoring Service, one of the Copernicus services, several high-resolution raster layers were developed. They are called Pan-European high-resolution layers, and they provide information on specific land cover characteristics. The HRLs are a result of automatic processing and interactive rule-based classification. Since 2015, They are produced with the use of time series from a number of different sensors, including the combination of the optical and radar data. The main source are Sentinel satellites. The catalog of high-resolution layers includes imperviousness, forests, grasslands, water and wetland, and small woody features. These thematic layers can provide input for detailed analysis of the urban area in relation to green infrastructure and biologically active areas. All layers can be downloaded from the Copernicus service website. Satellite data has many applications. We have also Copernicus Climate Change Service, but also Land Service and others support, all of them, they support the adaptation and mitigation climate policies of the European Union by providing consistent and authoritative information about climate change. Development of the climate adaptation strategy for the city of Warsaw, undertaken within Live Adapt City PL project 2-3 years ago, was partly based on satellite image analysis. And here we'd like to show you some dedicated thematic maps produced and presented in a dedicated album, Warsaw from Space, maps which are maps coming from databases coming from the Earth observation, which were a starting point for development of the climate adaptation strategy for the city of Warsaw. Here we have some examples of databases supporting the creation of adaptation strategy. The typical example is a land cover. So Urban Atlas or Korean land cover are the examples. The Urban Atlas is on the left, and that was one of the main sources of information. The pink areas, which you can see on the right side on picture B, show serious changes of land cover occurred between 2012 and 2018, like new roads, new housing areas, and others. Okay. Another example of analysis that uses Earth observation data is the creation of maps that show impermeable surfaces and biologically functional surfaces that are important for climate change adaptation. Such kind of maps can help to identify the areas of urban heat island or areas at risk of flooding. Such data can also be correlated and analyzed with other spatial data like population density, rainfall measurements, or flood risk. Important information derived from satellite images refers to change detection of permeable and impermeable surfaces in the city. The map on the left shows decrease of the biologically functional areas in the period 2006-2014. And on the right side, you can see the decrease of biologically functional area in a small part of the city in just 2 years, caused by the development of residential buildings. So this type of information can be easily registered. The direction and level of changes are very unfavorable in the context of climate change. It can result in the intensification of the urban heat island effect, and additionally in the impermeable surface will have an impact on local floods. Satellite data can also be used to visualize various types of indicators related to vegetation, water, or soil. Here you have the example of the map showing the NDVI normalized difference vegetation index. The NDVI is an indicator of the quality of plant vegetation, ranges from -1 to 1, where -1 means no vegetation, and 1 indicates areas covered by vegetation of good condition. It is considered that the green area is in a good condition if the NDVI index is above 0.6. So like in fact, most of the parks in Warsaw have the NDVI above 0.6, are in a good condition. Another indicator is the normalized difference infrared index, which allows to measure water content in plants. And the value of NDII increases with the increase of water content in the plant. This indicator and many others were calculated with the use of data from different satellites, but particularly Sentinel-2. All indicators maps are available online. At the end of our webinar, you will we'll give you the link to places where you can look at this data and download also most of the maps. And here comes the last example, map of surface temperature and map of albedo. The surface temperature map shows places heating up easily and those heating much slower. Detailed analysis allow to select places recommended for additional greenery or green roofs in areas of intensive urban development. Green infrastructure have a positive impact on the local climate and perception of temperature on the hottest days in the year. And as you know, the number of days with high temperature increases from year to year. To summarize, using satellites, we can monitor changes and promote the responsible use of land and natural resources to protect our ecosystems. Satellite data give us many analytical possibilities in the context of greenery management. On their basis, we can identify and classify different types of green areas in the city and analyze their arrangement. We can estimate the size of these areas and in the next years observe trends of changes. We can also analyze the availability of this greenery for citizens and study its condition using various indicators such as NDVI, NDII, and others. However, the management of greenery in the city is a local issue that requires data with a high level of details. And in the case, aerial images with a resolution of 1 or half a meter may be a better solution for those detailed analyses, especially analysis coming with some specific attributes. Their characteristics and advantages are the same as those of satellite images, and at the same time, the detail of this data gives great possibility for their use in urban greenery management. Therefore, in the next part of this webinar, we'll present you a case study based on analysis made for Warsaw on how the remotely sensed airborne data enable creation of the tree crown map in Warsaw.
Okay, thank you very much, Maria, for a very interesting presentation. And before opening the floor for discussion, I would like to, as Maria said, tell you a few words about this case of Warsaw case study, which is focusing on the tree map crown. Okay. I have a problem too. Okay, now it works. To start with, I would like to tell you a little bit more about urban greenery management in Warsaw. So in my opinion, it is a very interesting case and very good example to to present. From perspective that Warsaw really takes care about urban greenery, at least in my opinion, and at least for the last few years. To start with, only a few years ago, they created a document, which is Declaration of Tree Rights. This is pretty much a manifesto of city authorities, which wanted to show that they believe that trees, as citizens, as everybody, also has rights. So, for example, trees have rights to be properly maintained. Trees has the right to grow in the city, and so on and so on. Later, as a next step, there was also created urban greenery guidelines. So experts have prepared guidelines which are supporting management conducted by urban greenery managers. So, for example, there is kind of standards how to for example, maintain capped trees, what tree species should be planted, and so on and so on. Then, as the next step, there was tree-crown map, which we'll be discussing today, together with another map, which is tree trunks location map. And this is basically collecting the way of collecting information for as many trees as possible in the city. And at the end, as a last step, is tree risk management, which is a special formula which is used in the software, or yeah, we can say it's like a software which urban greenery managers are using in Warsaw in order to know when to conduct inside, like in situ tree inventory of selected trees. So basically, when we know what is the condition of each tree in Warsaw, if it's great condition, there is no need to go there every week and check how is it performing. But if the condition is bad because it was already investigated, then this software gives information, you should visit the tree next time in this and this amount of time. So now we can talk about this tree-crown map in detail. So it's basically, we could say, kind of like a cascade. So first of all, we have information about location, height, and size of tree canopy. Then the second step, if we have the first one, then we can get the second one, which is taxonomic affiliation of species. So basically what species we have for these trees, which you had information about location, size, and so on. And as the next layer, if we have the first two, we could also get information about canopy health. So how the tree is performing. And at the end, we have this tree-crown map, which is also available online for city dwellers. So there are information about trees in Warsaw, which helps also management of the urban greenery from perspective of urban greenery managers, because people can really see that some trees are in bad condition, and that's why we have to cut them down. It's not like there is no reason for that. And also it can be justified there. There can be information like new supplementary plantings will be there. That means that people raise the awareness and they're not afraid of this action. So more technically, how it was conducted. So it was developed with the use of aerial remote sensing in January. So not drone, not satellite. Satellite could be possible, maybe not to get all of these extra layers, like extra information like tree health or tree species, but to get basic information about tree location and so on, it could be potentially enough. But it was important for city authorities that they have more precise information. That's why they went for this level of precision. So as I said, it's aerial remote sensing. And the analysis included, there were 3 types of remote sensing data and data obtained from tree inventory. What does it mean? First of all, there was like airborne laser scanning, so LiDAR, right? And this scanning showed us where exactly the trees are growing, their height and size and so on. Then the second kind of scanning was hyperspectral imaging, and this one was only used to support the first information about what the size of the tree and they're located. So this information was not used in any like processing of data, but just to check what they found is correct or not. And the most advanced scanning here was multi-spectral imaging, which allowed together with tree inventory conducted inside. So at the same time, people went and collected information about some trees, and they combined this information in order to show what for these trees which were located and the size were found out before, what is the tree species and what is the condition. So machine learning basically was used to combine this data which were from the field and data which were from this multispectral imaging. And that's why we found this extra information. So what was included in this preparing tree-crown map? So as I mentioned, we always have to conduct the tree inventory. So the work of people who are good at biology and so on is always needed still. But instead of conducting it for whole city, as I mentioned during my first presentation, which would be basically impossible, here we only have a sample. So the sample was basically 23,606 trees. And some people could say it's quite a lot. But when we think about it, that it's actually 0.5% of the trees which later we got information about. Or you can say that it's 1 per 300 of trees which you have to get information about, or 1 per hectare. Then it doesn't sound so much anymore, right? And then why it was information about 3 million of trees, but why it was estimated that there is around 9 million of trees? Obviously, because of the logic of the whole collecting data this way. So canopy is visible only from aerial perspective, from up. And that means that if there are like small tree growing below the canopy of another tree, this way we are not able to collect the information about the small tree. But this is mostly the issue for trees which are growing like in dense areas like a forest. So not really in the city center, also sometimes, but mostly like city forests on the suburbs of the city. Also, it's not all the trees which are included using this technology, because the smallest trees are not taken into account. So trees which are shorter than 3 meters are not taken into account, or if the canopy area is smaller than 7 meters. So let's now discuss about these 3 types of data, as I said, like cascade, and how we can use them. So the first one, which is the easiest, let's say, to obtain, also to some extent using satellite data, is location, height, and size. So we can find out what the number of trees, canopy size, and total canopy area, and how we can use this data. First of all, we can find out where are the regions where there is the smallest amount of green areas per one inhabitant, and we should maybe invest in greenery in this area of the city. Also, the most precious trees. What I mean here by precious is for instance, for this region, which is in the map on the right, this is part of the district in Warsaw, which is Żoliborz, which is the smallest district in Warsaw. And there we checked what was the tallest tree, and we found that it was 37 meters tall. So it's very tall, and maybe this kind of very interesting trees, because the tallest, the biggest, and so on, which are very precious from perspective of ecosystem services, because basically the biggest tree, the largest stream of ecosystem services provided, maybe it's worth going there, checking how this tree is going and doing, and so on and so on. The same it can help for supplementary plantings, because when we see that there are some streets with trees, but there are some gaps, maybe that's an idea for us that we should go there and think about making it complete. Also for new investment, because if you are thinking about new investment, maybe it's better to look for space which is not occupied by trees, especially these precious trees, and we can find some which is better, and so on and so on. But in this case, now I would like to also tell you more how we can use this data for adaptation to climate change, because that's what we are focusing today. So it can help for. So there will be these 3 ecosystem services, which I mentioned at my first presentation. So for example, local climate control. So we can combine data from this, let's say, tree-crown map, how it was in Warsaw conducted, with surface temperature maps, which are available like from satellite data as well. And we can find a spot, which first of all, they're very bad from perspective of heat, which they are producing, absorbing and basically radiating, but also combine it with the fact that there is no greenery at all. And for example, we could find one of spot like that, and this is actually a municipal bus company, which means it's owned by the city, by municipality, and therefore it should be quite easy to imagine that we can do some work there to change the surface, which is there, impervious surface, or maybe at least put some trees in the pots nearby, so the urban heat island is not that suffer. The other thing is like energy conservation. So as we said before, this is like again, in the Żoliborz district, a little exercise we have conducted for one building and two streets growing next to it. One is basically Tyria cordata, which is in English small leaf lime, if I remember well, and the second one is Robinia pseudoacacia, so in English it's black locust. And then if we take a look how they are interacting with the building, we could basically find out that one of them is providing benefits to the building because it helps with mostly with air conditioning issue, but the second one also, even though it can help to cool down the building to some extent, but because it also is shading a lot from the south also, so even in the winter time it provides shade, actually the net benefit is like minus here, so it generates more cost. So this kind of information in some areas, especially when we are thinking about planting street trees, which have some interaction with buildings, when we really think what will be the size of that tree, what should be the distance, this can also provide us with extra information, like knowing what's infrastructure in the city and where we want to plant trees, to make sure that we also optimize it in perspective of energy conservation. And the last one was stormwater control, right? So here, when we combine information about impervious surfaces in the city together with tree crown map, we can find out spots which, first of all, they're without trees, but without trees doesn't mean that anything has to be done there, because it can be still pervious surfaces. So the first red circle here, which we see, is basically housing estate. And even though there are not trees there yet, or maybe they are, but as I said before, maybe they are shorter than 3 meters yet, because maybe they were just planted, and that's why we don't have this data on the map. But even if there are no trees, it's still, if we are thinking about preventing this area from floodings, it's not that important, because there is like impervious surfaces which will maintain, like absorb quite decent amount of water anyway. But the second region, the second circle, red circle here, is parking lot, which is free of trees, but also full of impervious surfaces. So from that perspective, maybe that should be priority for reclamation, or basically to take a better look at this space and introduce there more greenery, in case if we are really interested in this region to protect the city from floods especially. And now the second type of data which I mentioned, which were a little bit more precise and not so easy to obtain, but if we have information about taxonic difference, about basically what are the tree species in the city, we can use it. So for example, here we see that in this region, we have 35% of Acer negundo, which is box elder in English, which may be a little bit too much. I mean, it's always good if there is like more tree species which are existing in the city, which are growing there. It's not more than maybe 10%. That would be optimal in some books, but maybe more. But 35 seems to be a little bit too risky. So in case if some pests will come and we will have problem with these tree species to survive, so then we are losing 35, which is plenty of total urban greenery in the region. So this can be somehow information from that perspective. But also we can take a look what tree species, or at least generally what category of trees, like deciduous trees or conifer trees we have, and based on the literature we know how they're dealing with certain environmental, like certain habitat. And for example, we know that conifer trees are not really dealing well with air pollution, and they shouldn't be in general planted along main streets or busy streets, or even at all street trees. They shouldn't act as street trees. So from that perspective, when we take a look, we see in case of Żoliborz, it's actually okay. There are no conifer trees which are street trees. They're mostly inside, like farther from the street, and so on and so on. But we can especially take a look also from perspective of adaptation to climate change, what are tree species now, and if they are in the literature famous for that they can handle, like urban heat island, like very high temperature, like some other things like very heavy rain events and so on, which are typical for what cities will be dealing with in the future because of climate change. So to better adapt to climate change. And at the end, if we really have this super exact information, like Warsaw managed to get about health of each tree in Warsaw, then we can conduct this analysis by ourselves. We don't have to take a look on the literature, what's generally recommended, what's not, but we can check how our trees are performing in our very specific microclimate situation. And here we see, for example, that Aesculus hippocas tanum, so in English it's horse chestnut, if I am correct, then some of these trees which are growing a little bit farther from the street, they are performing great. But if they are basically growing even in the park, but close to the street, or if they're street trees, then the condition is very bad, or most of them actually are dying, or they already be dead. So from that perspective, we can take a look at the tree species we have, where, in which region of the city even, or habitat type they perform the best, knowing also challenges of climate change which are growing for each city, and then we can make the most rational decisions if we analyze this data which we have. So that's shortly what I wanted to say about this case study. And now I would like to just tell you that it's not everything which we would like to tell you, but that's what the time constraints allow. So if you'd like to learn more, please visit the websites which are presented on this slide, for example, about Sentinel-2, about Warsaw tree-crown map, about Copernicus data as well, and some additional reading which is available here, and it will be available to you as well. And we would like to thank you very much for listening, as we would like to open discussion to hear your questions, and hopefully we will be able to answer them. Thank you.
Okay, thank you, Zbyszek, very much. So if you have any questions, and if we could give you some more detailed information, so please do not hesitate to ask. I see that it's 20 past 5 p.m., so that's quite a late afternoon, but I still hope that you have energy to ask. So we have one question from Lily Stenson. What programs are used for analysis and presentation? Well, I don't know to which part of the webinar you are referring to, because those programs which were used for the analysis of Sentinel data, these are typical image processing software, and we are not doing this type of analysis here in Grid Warsaw. So those analyses were created and prepared for the purposes of the development of the strategy on climate adaptation. And maybe you can say something, Zbyszek, about
Yeah, I mean, again, it depends which, if you could a little bit specify your question, because it depends on the analysis you're asking for. For example, when we are talking about this influence of trees on energy conservation, there was one software we used. For example, it's called i3 Design. So there are like one family of softwares, but most of this were conducted using some GSI analysis, like basic ones. So it all depends which exactly analysis would you have in mind.
And we have also another question about the Albedo, which was prepared and analyzed for the city of Warsaw. In fact, I can't just answer these questions directly, but Julia will come back with the answer to you. So you will try to find out and this detailed information, and we'll provide you with the information. Yes, the webinar, there's a question from the anonymous attendee. The webinar will be available, it's recorded, so it will be available on the EO4GEO site. You can come back and listen to it once again. Do you have any additional questions? I think that's not only that's an extremely interesting topic. As you heard, all cities with the number of population above 20,000 people will have to prepare their greenery plans. So for this type of analysis, then the use of Earth observation will be crucial. And the examples which we showed you are two different approaches. So the first, which is based the analysis for the whole city based only on satellite data, and the second one, which is much more detailed, and it's not only about the size of objects, but that's also the amount of other attributes was developed thanks to the use of airborne data.
What I can maybe also add is that we really think it's the future of urban greenery management. I mean, obviously, the more data we have, the better, because you can really make it more precise. And then this work which was done, why it was not done before? First of all, because of some technological issues, it was not that advanced. But second of all, like many years ago or some years ago, but second of all, the cost of it. But now, as it will be more and more popular, both of this, like technology is already there. So now it's the issue also of cost, which obviously actually the Warsaw case for this Warsaw three-cron map was the first city, as far as we know, which has conducted this exercise. And I also think it's very important to mention who was responsible for that. So it's the company called MGGP Rio, who were creating this map for Warsaw. And we know that they're planning to make it also more popular, because also as building the whole system for the first time was expensive, but now multiplying it is way cheaper. That's why we really think it will be the future of urban greenery management and conducting inventories.
Okay, so I think that we can close this webinar. So thank you very much for your attention. Please fill in the questionnaire, which is available in the chat, but also look at the recorded webinar, and please visit the EO4GEO website. Look at the training material catalog and training actions. There are a lot of extremely interesting materials and also tools, which I'm sure will support your activities, professional, and just can be interesting for you. Okay, so thank you very much, and
thank you very much.
Have a good the rest of the day.